friends, welcome to my lecture on various types of graphs. It is second lecture on various types of graphs. Let us first define union of two graphs. Now, let us first define union of two graphs. Let G1 be equal to V1 E1, G2 equal to V2 E2, then the union of G1 and G2 denoted by G1 union G2 is the graph G3, okay, which is the union of vertices of B1 B2 and the union of edges of E1 and E2. So, the vertices of G3 are the union of B1, the union of the vertices of B1 and B2, and the edges of G1 G3 are the union of the edges of E1 and E2. Now, we can see that in G1 B1 is equal to E1 vertices are B1 B2 B3 B4 B5, okay, and E1 is equal to E1 E2 E3 E4 and E5, and G2 consists of vertices B2 B3, the vertices are given by V2. B2 equal to V2 consists of vertices V2, V3, V5, V6, okay, and E2 consists of E5, E7, E8 and E9, okay. This is E7. Okay. So, when we consider B1 union B2, B1 union B2 will be the union of the set of vertices of B1 and B2. So, B2, B3, B5, B6. So, B6 will add because B2, B3, B5 are already there. Okay. So, B1 union B2 will be the set B1, B2, B3, B4, B5, B6. And E1 union E2 will consist of E1, E2, E3, E4, E5, after E5 we have E7, E8 and E9. Okay. So, now let us see, we have between B2 and B3, okay, we have edge E3 here, okay. Here we have the edge between B2 and B3 as the edge E9, okay. So, when we take the union, okay, between B2 and B3, we also consider E9 apart from E3. So, this is E3, and this one is E9. So, there are two edges E3 and E9 between B2 and B3. So, they are parallel edges, and then at B3 we have the edge between B3 and B6, okay. So, we add this, this is B3. So, we add this edge at B3, okay, B3 B6 we add this E7, okay, and from B5 to B6 we have the edge E8. Remaining figure is the same. So, we have added, when we have considered the union of G1 and G2 between B2 and B3, we add the edge E9, okay. So, that means there are parallel edges E3 and E9, and at B3 vertex and at B5 we add the edge E7, this is E7 and E8, okay. So, B3 B6 is connected by E7 and B3 B5 B6 are connected by E8. So, that is the union of G1 and G2. Now, the intersection of two graphs, G1 equal to V1 E1, G2 equal to V2 E2 denoted by G1 intersection G2 is the graph G3, where we take the intersection of B1 and B2, okay, to get the set of vertices of G3. So, the set of vertices of G3 is obtained by taking intersection of B1 and B2, and the set of edges of G3 is obtained by the taking intersection of E1 and E2. The vertex set of G3 consists of only those vertices which are present in both G1 and G2, and the edge set of G3 consists of only those edges which are present in both G1 and G2. So, let us take the intersection of the graphs we have considered earlier G1 G2. So, B1 intersection B2 if you take here, then B1 intersection B2 turns out to be see what is common B1 B2 B3. So, B2 B3 B2 B3 are there and then B4 B5 okay B5. So, B1 intersection B2 is equal to the set consisting of B2 B3 B5 B2 B3 B5 and E1 intersection E2 gives us the set of edges of G1 intersection G2. So, E1 intersection E2 will consist of E5 here and E5 here. So, that is the only edge. So, E5. Okay. Now, you can see here B3 and B5 are joined by E5 okay, and here also B3 and B5 are joined by E5. So, when you take the intersection of G1 and G2 you get B3 and B5 are joined by this E5 okay, and B2 which is here okay, and here okay, it occurs as an isolated vertex okay. So, B2 is here and B3 B5. So, this is the graph of G1 intersection G2 where B2 is an isolated vertex and B3 B5 are joined by the edge A5. Now, ring sum of two graphs. The ring sum of two graphs G1 equal to B1 E1, G2 equal to B2 E2 denoted by G1 ring sum G2 is the graph G3 equal to B1 union B2 E1 union E2 minus E1 intersection E2. So, the set of vertices of G3 is the union of the set of vertices of B1 and B2, but the set of edges of G3 is obtained by removing the edges that are common to E1 and E2 from E1 union E2. So, that gives us the ring sum of two graphs G1 and G2. So, let us see here B1 union B2 we had as in this example B1 union B2 was B1 B2 B3 B5 B4 B5 B6 okay. So, B1 union B2 is equal to B1 B2 B3 B4 B5 B6 okay, and what is E1 union E2 minus E1 intersection E2 okay. So, this is equal to E1 union E2 is this one E1 E2 E3 E4 E5 E7 E8 E9. E7 E8 E9 minus E1 intersection E2. It is E1 intersection E2 is E5. So, we get E1 E2 E3 E4 E7 E8 E9 okay. So, we have all vertices B1 B2 B3 B4 B1 here B2 here B3 here B4 B5 B6 all of them are there. We have to from E1 union E2 we just have to remove E5 okay. So, in this is E1 union E2 okay, this is E1 union E2, from there we have to remove E5. If you remove E5 this edge will be removed okay, and we will have this figure okay. This was E5 which we have removed okay. So, this is E5 is removed and we get the figure for even this G1 the ring sum of G1 and G2 okay. Now, decomposition of a graph G is said to be decomposed into two subgraphs H1 and H2 if H1 union H2 is equal to G and H1 intersection H2 is equal to a null graph. In other words, every edge of graph G occurs either in subgraph H1 are in subgraph H2, but not in both H1 and H2. Some vertices may occur both in H1 and H2. In decomposition, isolated vertices are disregarded. So, it may some vertices which are isolated may occur there in the case of H1 and H2. Okay. So, when you take the intersection H1 at intersection H2, when we say it is a null graph, there it might happen that some vertices occur there, but they are isolated. So, we do not count them and we call H1 intersection H2 to be a null graph. Now, let us say intersection, union and ring sum are binary operations, that is these operations have been obtained for a pair of graphs. When we have taken two graphs G1 and G2, we have defined their union, their intersection and their ring sum. So, they are binary operations, okay, in the set of graphs. Now, we discuss unary operations, okay, on a graph. So, by vertex deletion, if B I is a vertex in a graph G, then G minus B I denotes a subgraph of G obtained by deleting B I from G. Okay. Deletion of a vertex always implies the deletion of all edges incident on that vertex. Say in the figure here, if we delete the vertex B1, okay, if we delete the vertex B1, then this edge, this edge, this edge and this edge, 4 edges are incident on B1, they will all be removed, okay, to obtain G minus B1. So, the graph for G minus B1 will be like this. So, this is B6, B5, B4, okay. We have removed this edge has been removed, this edge has been removed, this one, and we have this, okay. So, B2 and B3, this one, okay. So, when B1 vertex is removed, the graph of G minus B1 is like this. Now, edge deletion, if EI is an edge of a graph G equal to V, then G minus EI is the subgraph of G obtained by removing EI from G, okay. That is deletion of an edge EI does not imply deletion of end vertices of EI. So, suppose we have this graph, okay, and we delete E1 from here, edge E1, okay. So, edge E1 is this one, okay, edge E1 is this is edge E1. So, when you delete edge E1, okay, only edge is removed, vertices are not removed, okay. So, we have this edge has been removed from here, okay, and we get this figure. This is the graph of G minus E1. Now, a graph which contains only isolated node is called a null graph, that is the set of edges in a null graph is empty, like here you can see null graph N4, okay. Null graph is denoted on n vertices by Nn. So, you can see here this graph for N4, there are 4 dots in this, no edge. Now, complete graph, a simple graph G is called complete if every vertex in G is connected with every other vertex, that is if G contains exactly one edge between each pair of distinct vertices. You take any two vertices, there is an edge connecting them, okay. A complete graph is usually denoted by Kn, okay. It should be noted that Kn has exactly n into n minus 1 by 2 edges, because each vertex, suppose in Kn there are n vertices, each vertex is connected to every other vertex. So, if any vertex will have n minus 1 edges, so total number of edges will be n into n minus 1 by 2, because an edge is counted twice, okay. If suppose we have a vertex this is another vertex, so this is joined to this, so it is counted once for this vertex, and when we come to this vertex, this is again counted. So, edge is counted twice, and therefore, the total number of edges will be n into n minus 1 by 2 in the case of a complete graph. Now, the graphs Kn, graphs of Kn for n equal to 1, 2, 3, 4 are shown here. This is K1, K1 means only one vertex, okay, and K2 means two vertices, so two vertices are joined by this edge. K3 means 3 vertices, every vertex is joined to every other vertex. So, there are these 3 vertices joined by these edges, and in the case of K4, okay, you can take, there are 4 vertices, okay, there are 4 vertices, every vertex is joined to every other vertex, okay. So, this is joined to this is joined to this, and this is joined to this, and similarly the other vertices. So, this is the graph for K4. Now, regular graph, a graph in which all vertices are of equal degree, okay, is called a regular graph if the degree of each vertex is r. So, that means there are n r edges at each vertex which are incident on it. The degree of each vertex is given to be r. So, if there are r edges incident on each vertex, then the graph is called a regular graph of degree r. Okay. So, when each vertex of a graph has equal degree, say degree is r, then it is called a regular graph of degree r, and every null graph is a regular graph of degree 0. The complete graph k n is a regular graph of degree n minus 1, because in the case of a complete graph, every vertex is joined to every other vertex. So, every vertex has degree n minus 1. Okay. So, every complete graph is a regular graph, complete graph k n is a regular graph of degree n minus 1. Now, if G has n vertices and is regular of degree r, okay. So, then the number of edges will be r n by 2. Okay. So, you have vertices, okay, say 1 2 these vertices, then if this vertex, each vertex here has degree r, then and there are n vertices, then n r by 2 will be total number of edges, because the by handshaking theorem, where we say that every vertex, this edge which joins this vertex to this vertex is counted for degree here as well as for degree here. Okay. So, when it is of degree r, okay, this edge is counted towards degree r for this vertex as well as towards degree for this vertex, and therefore, total number of edges will be r n by 2. So, in the case of this, see, this is regular graph of degree 2. You can see every vertex has 2 edges incident on it, this one here, this for this vertex, this one for this vertex, this one. So, each vertex here has degree 2, here again each vertex has degree 2, here also each vertex has degree 2, and here also each vertex has degree 2. So, they are regular graphs of degree 2. Now, suppose r is an odd integer, okay. Let us say r be an odd integer. Let us show that an r regular graph must have an even number n of vertices. Suppose S be the degree, sum of degrees of an r regular graph. Okay. R regular graph means each vertex has degree r. Okay. So, if S is the sum of the degrees of an r regular graph with n vertices, then S is equal to r into n, because the degree of, since the degree of each vertex is r and number of vertices is n, S is equal to r into n. Okay. Now, further the sum, we know that the sum of the degrees of the vertices of a graph is equal to twice the number of edges. Okay. So, twice the number of edges, and therefore, this is twice the number of edges. Sum of the degrees of the vertices of a graph is equal to twice the number of edges. So, S is an even number. Now, r is an odd number given. Okay. Therefore, n must be even. Okay. Since r is odd, n must be even. So, if r is an odd integer, an r regular graph will have an even number of vertices. Find those values of n for which the complete graph k n is regular. Now, every vertex in k n has degree n minus 1, because every vertex is joined to every other vertex. So, if there are n vertices, every vertex will have degree n minus 1. Therefore, for every n, the graph k n is regular of degree n minus 1, okay, because each vertex has degree n minus 1. Now, draw 3 regular graphs with 6 vertices. 3 regular graph means the degree of each vertex must be 3. Okay. So, you can see and 6 vertices must be there. So, 1, 2, 3, 4, 5, 6. So, this is a regular graph, 3 regular graph with 6 vertices. You can see at each vertex the degree is 3. Okay. Here also this is a 6, there are 6 vertices and the degree of each vertex is 3. Now, a bipartite graph, a graph GVE is called bipartite if its vertex set B can be decomposed into 2 joint subsets B1 and B2 such that every edge in G joins a vertex B1 with a vertex in B2. Okay. Every edge in G joins a vertex of B1 with a vertex in B2. In other words, a graph is bipartite if its vertex set V can be partitioned into 2 subsets B1 and B2 such that each edge in G has one end vertex in B1 and the other in B2, or GV is bipartite if V can be written as the union of 2 disjoint sets B1 and B2, so that no 2 members of B1 and B2 are adjacent. Now, let us see for example this graph. Okay. You see here there are 6 vertices 1, 2, 3, 4, 5, 6. These 6 set of 6 vertices has been written as set 2 sets of 3 vertices each. One is this one set of 3 vertices, another one is this one, a set of 3 vertices, and every edge of G, okay, joins a vertex of B1, vertex of this set to a vertex of this set. Okay. These are edges of G. This is edge of G, this is edge of G, okay, and this is edge of G, this is edge of G, this is edge of G. Every edge of the graph G joins a vertex of B1 to a vertex of B2. So, it is a bipartite graph. Complete bipartite graph, let G be a bipartite graph and B1 B2 be the partition of the vertex set V of G. Okay, like in the previous figure we have seen B has been partitioned into B1 and B2. Here the if GB is a bipartite graph and B1 B2 are form the partition of the vertex set B of G, the bipartite graph will be called complete bipartite if each vertex in B1 is joined to each vertex in B2 by just one edge. Now, here you can see this vertex is joined to this vertex by 2 edges, this edge, okay, and this edge, okay, they are parallel edges. So, this is not a complete bipartite graph. Each vertex in B1 is joined to each vertex in B2 by just one edge. So, then we will say that the graph is bipartite graph is complete. This graph is denoted by Kmn if this graph is denoted by Kmn if B1 has m vertices and B2 has n vertices. Note that the complete bipartite graph Kmn has m plus n vertices. Complete bipartite graph has m plus n vertices and mn edges. Okay. M vertices are joined to n edges. Okay. So, m vertices here are there, m vertices are joined to n vertices. So, we have every vertex is joined to every other vertex. So, if you take any vertex here, okay, it will be joined to n vertices here, and there are m vertices which are to be joined to n vertices. Okay. Each vertex is joined to every other vertex. So, total number of edges will be mn. Okay. Total number of edges will be mn and total number of vertices will be m plus n. Now, complete bipartite graph for example here. So, you can see there are 6 vertices, 2 vertices in B1, 4 vertices in B2, and every vertex here of B1 is joined to every other vertex of B2, okay, every other vertex of B2. So, total number of vertices are m plus n, that is 2 plus 4. So, 2 plus 4, this is m is equal to 2, n is equal to 4, and total number of edges is equal to m into n, that is equal to 8. So, there are 1, 2, 3, 4, 1, 2, 3, 4, total number of edges are 8. So, it is a complete bipartite graph. Now, this is example of K23, there are 2 vertices here and 3 vertices here, and every vertex here is joined to every other vertex here. Okay. So, total number of vertices are 5 and the total number of edges are 6, and here we have 3 vertices here, 3 vertices here, every vertex here in B1 is joined to every other vertex of B2. So, this is the example of K33. Thank you very much. So, that is the end of my lecture. Thank you very much for your attention.